let's talk about a very important idea called bootstrap resampling of data. In the previous segment, we had the problem of deciding what was the uncertainty in a quantity derived from some fitted parameters. And we saw two methods for doing that. In a sense, we're continuing that by looking here at a third method, but we'll see bootstrap resampling is a much more general idea. So let's kind of go up a level and think about what we were doing when we fit data to a model and then computed something. Well, as an end-to-end process, we started with a set of data points, measured values y sub I, each value measured at some position x sub I. We had a set of these, and we did some complicated procedure, which was model fitting and parameter determination, and we then computed a function of those parameters and we got out a number f. So we can view this as a black box. Now, this data set, if we're being frequentists here for a minute, this data set is drawn from a population of data sets that would obtain if we simply repeated the identical experiment. No two repetitions of the experiment would give the same data points, but what we're hoping is, of course, that they give values of f that are close to each other. That is to say that the uncertainty in f should be small. Unfortunately, we don't get to see the whole population of data points or data sets. We only get to see the one measured one that we have here. That's a sample of the population. What we'd like to do is draw new data sets from the population, reapply the whole end-to-end fitting process and calculation of the function f, and see the distribution of answers. So this would tell us something about how accurate our original answer on average should be expected to be. But we can't do this. We don't have access to the frequentists' population of imagined repetitions of the experiment. However, and here's the key idea in bootstrap resampling, the data itself is an estimate of the population PDF. In fact, the data itself is the only estimate of that population that we're ever going to get. So let's think about whether we can exploit it in some way. In bootstrap resampling, we use the one data set we have to construct many fake data sets of equal size and pretend that they are drawn from the population. Now, how do we construct a fake data set? Well, it's important what the size of a data set is, the number of points in it, because that, of course, determines statistical accuracies in various ways. So we draw from our data set a number of data sets with the same number of data points as in our original data set. Well, you say, how can you do that? Because if you draw the same number of points, you'll just be getting the same set over and over again. No, you draw with replacement from your original data set, so that sometimes you get a point more than once, and sometimes you miss a point. However, each of these produces a data set of equal size to the original one, and in a certain sense, it's a data set that came out of our only estimate of the population PDF of the data, namely the data set we have. So this might sound a little bit crazy to you, and for a long time many people and many statisticians thought so. But in fact there's quite a rigorous theorem about it, called the Bootstrap theorem. I'm not going to prove it in any technical detail, so we're glossing over the technical assumptions that go into the Bootstrap theorem. But roughly speaking, it says this: the distribution of any resampled quantity around its value that you get from your full data set estimates the distribution of your data set's value around the invisible population value. And estimates here, we'll just use it in a naive sense that asymptotically it has the same histogram as. So let's see how this works in a very simple example. Here's a data set we haven't seen before. It's 100 values of x drawn from some unknown distribution. And I'm showing you a histogram of those 100 values. Actually, there are 100 separate numbers. I could write them as a list. I've shown very narrow histogram bins, so only very occasionally do I get as many as 2 or 3 values that fall within a single bin. But you can see that the values are kind of concentrated between 1 and 3. Now, the bootstrap theorem applies pretty much to any statistic that we might happen to be interested in from this data set. So I've made up an oddball one just to show that it can be anything. Let's suppose that what we're interested in about the underlying distribution of these points is what is the ratio of their mean to their median. That's an oddball quantity. I can't think of any actual reason you'd want to be interested in that, but let's try it as an example. So here we are in MATLAB, and I'm just going to compute the quantity of interest from the data. MATLAB has a medium function, and the data is in some vector called sample. So the sample median is median of the sample. The sample mean is the mean of the sample, another MATLAB function. And the sample statistic, what we're interested in, is the quotient of those two. So what do those give? Well, we get this value for the median, this value for the mean, and what we're interested in is this value for the statistic, 1.0984. So let's remember that our actual data gives a value of something like 1.09. The question we want to ask is, how accurate is this? It's not obvious from anything that we've done so far whether the true value in the underlying distribution from which these points were drawn is the true value within 1/100th of 1.0984, or is it within 1/1000th, or could it be 1.2? How accurate is this estimate? Now I'm going to show you what you don't usually get to see. You don't usually get to see what the actual population is from which this data set was drawn. But since I made up this data set, it's a synthetic data set and I happen to know what it is. It happens to be a gamma distribution plotted here. In fact, this is by itself a histogram of a much, much larger sample that I drew, so that we can repeat this same calculation on this much, much larger, essentially infinite data set. The median is the median of this big sample, the mean is this, and the statistic comes out to be, here we are, 1.1222. So it turns out that this is inaccurate by something like 2/100ths. And what we're seeking is a way of being able to estimate that from just this data sample. So how do we do the bootstrap? We have 100 data points, as before, and I'm going to bootstrap 100,000 times. So what that means is, here's a loop. For each time out of 100,000, I'm going to choose a new random sample. And in MATLAB, there's an easy way to do that. It gives you this function, randSample, which, when you use the arguments like I'm showing here, returns a sample of integers between 1 and n data with replacement. So that sample of integers I'm going to call choose. And now within each bootstrap, I compute not the mean of the sample, but the mean of the sample indexed by choose. And since choose is a set of integers that can include repeats, sample is a vector of sample values in which some of those values are repeated. I'm interested in the mean divided by the median. And then let's plot a histogram of those bootstrapped values. So here it is. The mean of this histogram is 1.0928. That's essentially the same value that we obtained from our single data set. The reason it's slightly different is that I didn't resample that data set infinity times. I only resampled it 100,000 times. But here's the payoff on this. The payoff is we now get to see what the standard deviation of this bootstrapped resampling is. And we see that it's 0.06. So this is a measure of the accuracy that we should expect for this, our estimated statistic. So this is an estimate of the accuracy that we should expect to get in trying to measure the ratio of mean to median of our original data set of just 100 points. In other words, an estimate of the accuracy of this number 1.09. And what's pretty amazing is we were able to get this just from the internal consistency, as it were, of the original data set of 100 data points. Now you might be interested in what this looks like if I go over to this side where I'm allowed to know the hidden population. So here what I've done is I've repeated the same bootstrap calculation, but instead of drawing new data sets by resampling my original data set, I'm actually drawing each new data set as being a sample of the gamma function, random gamma function in MATLAB. And let's see what that histogram looks like. That histogram looks like this. And now we see that the true value is 1.12, and that the standard deviation that we would actually expect from data set to data set is 0.05 here. So the fact that this 0.06 is reasonably close to this 0.05 means that from our single data set, we were able to estimate pretty accurately what the range of answers would have been if we actually repeated the experiment independently 100,000 times. So here are some things to notice. First of all, on this side, where you have just your one data set and you're resampling from it, you can resample as often as you want, and you'll never improve the accuracy of this value, your desired statistic. You have only one data set, and there's only going to be one answer that comes out of that. The other thing to notice is that these two distributions are not identical. They have similar means and similar standard deviations, but they would only become identical in the asymptotic limit of the data set being very large, of our having had way more than 100 points in the original sample. There's nothing in allowing n-boot, the number of bootstraps resamples, that to become large that would bring these distributions close to each other. The reason that this data set has a different shape is because, in a certain sense, it's distorted by the peculiarities of the one particular data set we have. In this 100-dimensional space of these 100 data points, maybe we're just outlying into one direction or another, and that fact that it's a particular data set that we're bootstrapping on gives this a particular shape, which is different from the shape if we could actually have drawn 100,000 separate genuine data samples, that is to say, repeated the experiment 100,000 times. So let's go back and do the same thing, not to that little toy example, but to this slightly less toy example that we've seen in previous segments, where we drew 20 data points and tried to fit a model that had a hump in the middle. And we were interested in the area of the hump, which, if you recall, was the parameters b3 times b5. So here's the Bootstrap code to estimate the accuracy of that derived quantity b3 times b5. What do we have? Here's the loop over the number of Bootstrap resamples we're going to do, and here we're going to do only 1,000 because it's a more complicated process. And here is embedded that whole search for a chi-square minimum. In other words, you embed inside your Bootstrap loop the whole black box that takes you from the data to the value of the derived parameters, or rather here to the value of the derived parameters b3 times b5. which I'm going to put off in an array called vals. Now there's another bit of realism in this example that I want to point out. Because we're going to do this search 1,000 times on different draws of the data, we have to include the possibility that our nonlinear minimum finder here could run into trouble, because nonlinear minimum finding is not always guaranteed to have a success. So I've had to set up some parameters that apply to the MATLAB function fminsearch. And in particular, it's possible that this will fail and set a flag. And so if the flag is set for success, I'm going to save that value. And if the flag is set for failure, I'm going to instead save a value of 100, which signals that it was a bad case, and I'm not going to use that in my Bootstrap histogram. So then here I plot the histogram of the good values, values with values less than 2 that come out of that, and compute the standard deviation. This is what I get. You'll recall that B3, B5, when we computed it before, was a value something around 1. And we get a distribution that has a peak at something around 1. But we also see that it's very, very broad. In other words, some of the times when we resample this data set of 20 points, we get an area of the Gaussian which is as small as down here. And sometimes there were 4 off-scale values that went all the way up to 27 here. I didn't plot them because I wanted you to be able to see the details of this histogram. This was the actual data we got. What kind of sampling of this data could give a very small value of B3 times B5, or for that matter, a very large value? Here's an example that gave one of these points way down here so that you can see what happened. Notice that, as advertised in Bootstrap resampling, when there is a point down here, it corresponds exactly to a point up here. But what you can also see is that some points are missing. So for example, we have 2 points here and only 1 corresponding point here. Now, what you can't quite see on this picture is that whenever there is a missing point up here, then one of these resampled points has actually been chosen more than once, and it gets, in a sense, extra weight in the fitting when I do the chi-square fitting by virtue of being there. So the way I got a very small value here is we just happen to have missed out on some of these dots up here that would have given the peak of a larger breadth. And then when we combine that with the fact that some of these other points have double weight, we end up finding only this little puny Gaussian here. What about the other case? You might think it would be hard to get a huge area for a Gaussian with any resampling of this points. But look. What happens is, by chance, we didn't resample any of the points in here. And by chance, the points right before and going into that gap were rising, and here, going into the gap, are rising. So the fitting routine, rather stupidly in my opinion, fit this huge off-scale Gaussian here that had very large area. Well, there's a deep point lurking here, lurking in this histogram. We're trying to estimate the accuracy of this quantity B3, B5. And here, we seem to be using in that estimate of accuracy data sets that just had flaws in them. They just didn't happen to have the points here, and especially here, they didn't happen to have the points in the peak. And you can ask, is it fair to have our estimate of B3, B5 impugned by these data sets that just don't look like the real data set that we actually have in hand? And there's no simple answer to that question. That's a deep frequentist philosophical question. A frequentist would say, well, sure, in this example you can see that there's something wrong and you might be able to just throw that out of the estimate. But we're in a high dimensional space here. We've got 20 data points. How do you know there isn't something different, that's wrong with your original data, that you just can't visualize in some way? Why are you so sure that when you bootstrap, you'll be able to figure out which are the impugned data sets, which are the bad data sets, and then somehow narrow this distribution here and decide that you were really more accurate, that you were really somewhere in this distribution? So let's compare side by side these two techniques, one from the previous segment and one from this segment. In the previous segment, we learned about sampling the posterior distribution of B3, B5, and we got a histogram like this. In this segment, we've learned about bootstrap resampling, and we get a rather different looking histogram, although it still has a peak at around 1. Now, if we increased the number of samples of the posterior on this side, or if on this side we increased the number of bootstrap resamples, these histograms would not converge to each other. What would happen is that each histogram on its own would converge to a smooth curve. But this one would converge to a smooth curve that goes something like this, up through the data here and then down here. On the other hand, what the bootstrap theorem tells us about asymptotics is that if we increase the size of the underlying data sample from 20 xy points to a much larger number of xy points, and then repeated sampling the posterior to estimate B3, B5, or bootstrapping to estimate B3, B5, then those histograms, modulo some technical assumptions, would converge to each other. And that's the sense in which asymptotically sampling the posterior and bootstrap resampling do converge to the same estimates. But we're never in asymptopia. We always have finite size data sets. And in that case, each of these two techniques is a valid answer. They're just answering different questions. The frequentist imagines repetitions of the experiment, each repetition giving a different data set, and asks how much variation in B3, B5 would there be over those data sets. And then the justification of doing that process is that the frequentist says, look, conservatively, I shouldn't expect my experiment to be any better than a random draw from all possible identical experiments, and therefore I'd be kidding myself if I thought the accuracy was any better than that. The Bayesian says something different. The Bayesian says, look, I have exactly one data set. Here's what I'm interested in. It's the probability distribution of B3, B5 as determined by that data set. And that's really the question of interest. Because, maybe I got lucky and my data set just happens to be particularly good and really nails the parameters, whereas the frequentist's data set on average wouldn't be as good. So you see, these are simply different philosophical viewpoints.